In this tutorial, we will see how to calculate the nitrogen requirements of crop rotations using the theory that is contained in the chapters 24 and 25 of the book Principles of Agronomy for Sustainable Agriculture. In short, we will be calculating the requirements of nitrogen as a function of, or using this equation, which is subdivided in different components. The first one that we find is N, which is the nitrogen that we will have in the soil at the end of the cycle, also called the residual nitrogen. Usually we can adopt low values going from 10 to 70 kilograms per hectare, which is assumed to be the threshold for nitrogen uptake by plants or by crops. Then we need to consider the uptake of nitrogen by the crop, and this is calculated from the amount of nitrogen contained in the biomass, in the whole biomass of the crop itself. So we will have a component that depends on the roots. This parameter is the fraction of nitrogen in the roots in relation to the fraction of nitrogen in the above ground biomass. And we will consider the nitrogen content of the harvested organ and the residues. Then we should account for the mineralization of previous crop residues. And here we have an expression for calculating the mineralization of above ground residues coming from the previous crop, and a term that is accounting for the mineralization of the previous crop roots. For simplicity, we will be assuming that 100% of the root residues will become available. In turn, the mineralization of above ground residues will be calculated from a coefficient of mineralization, the fraction of residues that will be left in the field after the crop has been harvested, and the concentration of nitrogen in the residues of the previous crop. That's why we have this symbol here. Okay, with regard to the coefficient of mineralization, this can range usually, or usual values go from 0.9 to 0.5. We will adopt the highest value, 0.9, if we are working with residues coming from a legume under tillage. If the legume is grown in a no-till system, we will use 0.7, and this will be also the value that we will use for non-legume crops under tillage systems. Finally, if the crop is not a legume and the soil is not tilled, then we will use the lowest value, 0.5. This is a simple rule that we can adopt for giving values to this coefficient. The fraction of residues left in the field is an agronomical factor, it's an agronomical decision. And in this example, we will be leaving 100% of the residues in the field. Then we finally have here another parameter, which is N other, which represents the sum of inputs of nitrogen into the system through atmospheric deposition, through the water used for irrigation, and in the case of legumes, by symbiotic fixation. If we are working with a non-legume crop, we can use low values for N odor, going usually from 5 to 10 kilograms per hectare, except if also the water is particularly rich in nitrogen, of course. Finally, we have a final term, which is 1 less N, which represents the efficiency of the application of nitrogen fertilizers. And this difference will be accounted by losses of nitrogen as a result of volatilization, leaching, or denitrification. These values, this 1 less N, takes values that can go from 0.5 to 0.9, depending on several factors that can be agronomical, like the decision on which fertilizers to use, and also the interaction with the environment. If we have a lot of rain, we will have an increased risk of having leaching. Okay, so this is the equation we will be using for the calculations for estimating the nitrogen in the harvested organ or the residues. We will just have to multiply the dry yield by the content of nitrogen in the harvested organ, or in the case of the residues, the biomass of the residues by the concentration of nitrogen in the residues, which can also be derived from this expression. Let's see an example. Here we are going to consider a crop rotation of rapeseed, annual crop, and chickpea, a legume. This table shows the input data that we need to implement the equation. We have some common inputs for the two crops. So for instance, we will be considering that this residual nitrogen will be 10 kilograms of nitrogen per hectare. We will here consider that we are very efficient with the fertilizers, and we are going to use 0.9, which is this term, and we will be applying urea, which has a concentration of 0.46 kilograms of nitrogen per kilogram of the fertilizer. I have included a fictitious price to calculate the cost of the fertilization with this fertilizer. The data for the crops include the dry yield, the fraction of nitrogen in the yield and residues. This can be obtained from the book of Principles of Agronomy for Sustainable Agriculture, from the appendix of chapter 24 for a wide list of crops. We have also obtained information on the harvest index, the fraction of nitrogen in roots versus the aerial nitrogen. We are going to use the default value, which is 0.2. And well, mineralization coefficient in this case will be 0.7, because we are considering that we are making tillage, but rapeseed is not a legume. And yeah, the residues left in the field will be 100%. For chickpea, these are the data. Here the mineralization coefficient takes a 0.9 value, which is higher because this is a legume. And now let's proceed with the calculations in the second table. The nitrogen that is exported in the yield can be easily calculated for rapeseed as dry yield by the concentration in the yield. With regard to the residues, we need to apply this second equation. So we have the dry yield, the concentration of nitrogen in the residues, and this expression that depends on the harvest index. Okay. Then we repeat the same operation for chickpea. Oops, sorry. Residues. Harvest index, which in this case is the same in this example. Okay, now let's calculate the uptake. The uptake will be 1 plus the fraction of nitrogen in the roots multiplied by the nitrogen that is contained both in the harvested organ and the residues. 242 kilos. The mineralized nitrogen from above ground residues of the previous crop will depend on the data of the previous crop, which in this case is chickpea. And this will be calculated as the product of these three terms, which is the coefficient of mineralization of chickpea multiplied by the fraction of residues of chickpea left in the field and the nitrogen contained in the residues. For below ground is a matter of applying this other equation. We should consider both the nitrogen in the yield and residues of the precedent crop and the fraction of nitrogen in the roots. In the case of other sources of nitrogen, here we will consider that atmospheric deposition and irrigation leads to 10 kilograms of nitrogen per hectare. Now we can calculate for rapeseed the requirements of nitrogen, which will be the residual nitrogen plus the uptake minus mineralization and minus other sources of nitrogen divided by the efficiency. The requirements of urea in this case will be calculated from the concentration of nitrogen in the fertilizer, and the cost can be easily calculated from the requirements of urea and its price, 243 euros per hectare. In the case of chickpea, we are going to use exactly the same procedure. So the uptake of nitrogen by the chickpea will equal 1 plus the fraction of nitrogen in roots multiplied by the total nitrogen content. 140 kilograms per hectare. Mineralization will rely on the residues of the previous crop, which is rapeseed. So in this case, we should use for the above ground residues the mineralization coefficient and fraction of residues left of rapeseed, also their nitrogen constant, well, the nitrogen content in those residues, which is 61. And for below ground residues, we use the fraction of nitrogen that multiplies the sum of these two variables. So in total is 83 kilograms of nitrogen per hectare. Okay, in this case, the parameter of other sources of nitrogen in the system cannot be just the atmospheric deposition, because in this case we are working with a legume crop that is able to make a symbiosis with rhizobium and fix nitrogen itself. For making an estimate of the capacity of chickpea to fix its own nitrogen, we will use a table of the book of Principles of Agronomy, which calculates the percentage of the crop uptake that is obtained from symbiotic fixation. And we need to take into account whether we have soil with higher or lower contents of organic matter than 3%. We are going to stick with an organic matter content below 3, and we should go to annuals. And also we need to take into account the availability of inorganic nitrogen in the soil, which is in the interval between 55 and 110, as we have said before. So 80% of the crop uptake will be obtained from fixation. So this will be 0.8 multiplied by the uptake, which is 112. If we apply the equation, this leads to a negative value, so which is obviously impossible. This equation should be constrained so that it takes the maximum of the expression and 0. The requirements are 0 in this case, so there is no need to apply urea for chickpea.